So good afternoon, friends, and welcome back to the online learning platform at Department of Civil Engineering. I'm Rajesh Gopinath, and we are together for the course on environmental studies. And if you can recollect, in the previous session, we had discussed about acid rain, which is a form of environmental pollution. Okay, we shall continue the trend, and today we shall discuss another form of environmental pollution at the global scale, and that's ozone depletion. I would like to stress very clearly here that when I say ozone depletion, I am referring to stratospheric ozone layer. Okay. Now, friends, what we need to understand is, basically there are two types of ozone. One is the ground level ozone, that is what we are exposed to, and the other is stratospheric ozone. So in today's presentation, first I'll clarify the concept with respect to both of them, and then we shall speak about the factors which are responsible for causing stratospheric ozone layer depletion. We shall move on to the potential impacts. Okay, how can we go about controlling them? Then finally we shall summarize and list the references for your kind perusal. So friends, first let's have some basic understanding with respect to ozone. Now, ozone is basically a colorless gas, O3. Okay, like you say, oxygen is O2. Ozone is a gas which is made up of three oxygen atoms, O3. Now, ozone can exist even in the ground level and also in the upper atmosphere. So basically, as you can see on the screen, when I say upper atmosphere, we have different layers. This is something you might have studied in your geography. Okay, we have troposphere, that is the one which is we are closest to. Then we have above that stratosphere. Then we have mesosphere. Then we have ionosphere. Then we have thermosphere. Then we have exosphere, and wherein we have the beginning of outer space. Okay, friends, ozone can also exist around us in the ground levels. Okay, but please do not confuse yourself with tropospheric ozone and stratospheric ozone. The ozone that is around us is basically dangerous. It's a carcinogen. It can cause cancer when we are exposed to it. It can also be harmful for building materials and also for plants. For instance, it causes cracking of rubber. Okay, now we're not talking about that ozone. We are basically talking about the ozone which is located roughly around 15 miles from the Earth's surface. I am talking about that ozone which is present in the stratosphere. Basically, when we speak about stratospheric ozone, it's a gaseous umbrella. Okay, it's a layer of ozone which is present in stratosphere and is doing wonders for us. Now, what we need to understand is, in today's presentation, we shall try to understand how that ozone layer is actually formed, okay, how it is getting destroyed, and further so. So, friends, let us now try to understand how the ozone. The gentleman who was responsible for identifying the various reactions which explains how ozone layer is formed, his name is Sidney Chapman. Therefore, the equations which I'm going to present to you one after another, as you see, okay, these are famously called as the Chapman's reaction. Okay, friends. Now, basically, whenever we speak about ozone layer, in simple words, we are talking about three species. One is your ozone, O3, okay, as you see here. Second is your oxygen, that is O2. And the third is your atomic oxygen. These three are extremely important for presence of your ultraviolet radiation. In the presence of your ultraviolet radiations, there is formation of ozone taking place. Okay, how does it happen? Look at the second equation or the second reaction. In the presence of ultraviolet radiation, when your atomic oxygen reacts with oxygen, it results in the formation of ozone. Friends, the second step that you see, this is the major reason why we have ozone layer. Okay, but what we need to understand is you also see certain other equations or reactions. Okay, friends, when ozone is being created in your stratosphere, simultaneously ozone is also getting destroyed. Look at the equation or reactions in 3. So here, in the presence of ultraviolet radiation, ozone is splitting into oxygen and atomic oxygen. And if you see here, due to the attack with the atomic oxygen, ozone is splitting into 2 molecules of oxygen. So what I'm trying to tell you here is, in your stratosphere, naturally ozone is created and ozone is destroyed, and that is because of its reaction with ultraviolet radiation and the species such as oxygen and atomic oxygen. Friends, ultraviolet rays are responsible for the creation of ozone, and the same ultraviolet ray is triggering the destruction of ozone. These reactions that you see, which are famously called as Chapman's reaction, these are simultaneous reactions. So the beauty is, when ozone is being formed, ozone is also naturally being destroyed. But this is not leading to ozone depletion. Okay, because these are well balanced in the nature. There is an equilibrium which is maintained in these 4 reactions that doesn't allow ozone depletion to take place or ozone hole formation to happen. Now let us have some more knowledge with respect to ozone layer. Friends, ozone layer, okay, it is measured in Dobson units. Now, 1 Dobson unit is equivalent to 0.01 mm thickness of stratospheric ozone. Okay. Now, what basically happens is, ozone layer is usually very thin over the equator and very thick over the poles. Now, if we take the average measurement of ozone layer around the earth, it roughly comes around 220 Dobson units as of today or as of now. Okay, if in case your average thickness comes below 200 Dobson unit, then it is called as ozone layer depletion, or it is called as ozone hole formation. It is always good if we can have the average thickness of ozone layer as around 300 Dobson units, or in other words, 3 millimeters. Okay, now what is the importance of this ozone layer? This ozone layer is very helpful because it blocks the harmful ultraviolet radiation which enters the Earth's atmosphere. So now look at the sarcasm. The ultraviolet rays, which is responsible for creating your ozone layer, the same ultraviolet ray which is responsible for destruction of ozone layer in a natural, sustainable manner, the same ultraviolet ray is being blocked from entering the Earth's atmosphere by these ozone molecules. Okay, so as long as you have got ozone layer, we are pretty much safe from the harmful effects of UV rays, which may be ionizing and non-ionizing, from entering the Earth's atmosphere. But now what's happening is, okay, due to certain chemicals, okay, such as oxides of nitrogen, bromides, and chlorofluorocarbons, or popularly termed as CFC, they are triggering the destruction of stratospheric ozone. Okay, now as a result of which, ozone hole is getting widened, ozone depletion is becoming rampant, and probably the first time that we discovered the ozone hole was over Antarctica in the year 1979. So friends, if I would have to define what is ozone hole formation or ozone layer depletion, this is how I would put it across. Ozone hole formation or ozone layer depletion can be defined as, first, the destruction of stratospheric ozone by ozone depleting substances such as bromides, NOx and CFCs. And second one, the disruption. I will repeat, the disruption of the equilibrium which exists in the Chapman's reaction. So friends, what I'm trying to suggest is, when we say ozone hole formation, two things are happening. One, the ozone in the stratosphere is getting destroyed. Okay. Secondly, the balance that you see in this reaction, in the Chapman's reaction, that is getting hampered. So these two collaboratively is resulting in ozone layer depletion. Okay, now let's try to understand something more about ozone depleting substances. Friends, now usually when somebody inquires, or probably what you might have read across in various media channels, okay, whenever you associate ozone hole, okay, whenever you try to link ozone depletion, automatically the word which comes to our mind is CFC, chlorofluorocarbon. But what I want to tell you today here is, CFC is just the tip of iceberg. Okay, there are chemicals which are much more dangerous and fatal than CFC itself. I do agree that one CFC molecule can destroy 1 lakh ozone molecules. I will repeat this. One CFC molecule can destroy 1 lakh ozone molecules. But do you know what NOx does? It has the potential 20 times that of CFCs. Bromides, it has a potential 40 times that of CFCs. Okay. Now, how would oxides of nitrogen, destroy your ozone layer? Friends, when you basically talk about your layers of atmosphere, okay. Now, typically, if you have taken a flight that is in your passenger airlines, basically it flies at your upper troposphere, and then you have the jets which fly at the lower stratosphere. So basically, you know that your jets or your space shuttles or your rockets, okay, they use liquid nitrogen. Now, when the liquid nitrogen burns, automatically it produces what is called as oxides of nitrogen. So probably, yes, all the oxides of nitrogen is being produced very close to the ozone layer. But still, the blame always comes for CFCs. Why is that? Let's try to understand that. So friends, let's take an example. Okay, CFC, chlorofluorocarbon. If you have not heard much about it, let me tell you. The gentleman who discovered CFC, that is Thomas Midgley, okay, when he discovered it, he got a Nobel Prize for it, because this was a miracle chemical. And why is it a miracle chemical? Because it found application in various types of industries. Coolant, solvent, refrigerant, insulant, you name it, you can use it. Okay, it's like a Swiss knife, multiple uses. And not just that, the best part is CFCs are not hazardous. What do you understand by not hazardous? It cannot catch fire, it is not radioactive, it is not corrosive, it is not toxic, it is not explosive, it is not even reactive. CFCs are basically inert chemicals, totally inert. They do not react with anything. Okay, but let's try to understand why the blame game is always with CFCs. Okay, let's take an example. Friends, let us say a CFC molecule is released in your troposphere, that is during your industrial application or your residential application. So when CFC molecule is being released, let's take only one molecule as an example. Let us say one CFC molecule is released in your from your fridge or your refrigerator. Okay. Now, basically CFC molecules are very heavy. Okay. Now, usually what would happen? It has to rise in the atmosphere. So it may take very well around 2 years to 5 years to move up and reach the ozone layer. That's roughly about the time it takes, 2 to 5 years. Okay, once it reaches there, for the remaining 95 years or 98 years, it will remain there. So what is the meaning? The meaning is CFC molecules have a lifespan of 100 years. Okay, let it be. Let that be, because you know very well that CFC molecules are inert. So when they are inert, they will not undergo any reaction. Now, this is what we need to understand, a small twist. Okay, Friends, when the CFC molecules reaches the stratosphere, reaches the ozone layer, it does not do any harm because it is inert. It is a non-reactive species. But then something comes into play. Ultraviolet radiation. The same ultraviolet radiation which helps in formation of ozone layer, the same ultraviolet radiation which helps in natural sustainable destruction of ozone layer, okay, the same ultraviolet radiation which is being prevented from entering into the earth's atmosphere, the same ultraviolet rays, when it strikes the CFC molecules, okay, it converts your CFC molecules from a stable species to unstable species. It converts it by providing energy from inert to reactive species. And as an outcome, this unstable CFC molecule, to attain stability, has to lose energy, and it does that by losing a free radical of chlorine. Friends, I would request you to look at this first reaction. So a CFC molecule, when impacted by ultraviolet radiation, it breaks up into a free radical of chlorine in order to become stable. So this has become stable now by releasing a free radical of chlorine. So what next? This one free radical of chlorine goes and knocks or goes and destroys one ozone molecule, producing oxygen and one more free radical, as you can see on the screen. I will repeat this. In the step number 1, the CFC molecule, when impacted by UV rays, becomes unstable, and to become stable, it releases a free radical of chlorine. In second step, this same free radical of chlorine, okay, goes and hits one ozone molecule and produces oxygen and free radical. Now understand, it is the second step where ozone destruction has taken place. It is in this step that the ozone has been destroyed in a very similar manner to these reactions. Okay, now what is next? This free radical that you see here, this is again a unstable species, and to become stable, it has to lose energy, and what it does is it again breaks up into an atomic oxygen and another free radical of chlorine. So in this third reaction, this unstable species breaks up into atomic oxygen and free radical of chlorine. My dear friends, this free radical of chlorine will go on destroying at least 1 lakh ozone molecule in its lifetime. So it is this free radical of chlorine that we are referring to CFC, which is responsible for destroying 1 lakh ozone molecules. You might very well tell me that in this reaction, I also have the production of oxygen and atomic oxygen. Oxygen plus atomic oxygen gives ozone. Friends, what we need to understand is, in the Chapman's reaction, yes, ozone formation, ozone depletion takes place same time, but there was a time gap. Okay, the time gap is probably in few seconds, let's say 5 seconds. And that 5 seconds, imagine how many lakhs of ozone molecules are being destroyed. So this is not a sustainable breakdown. So it is because of the temperature factor, it's because of the time lag. Even 1 second would make a huge difference now. It is because of these combination of reactions and factors that ozone hole is becoming widened. We are not giving it sufficient time to recover. So friends, this is the chemistry behind destruction of stratospheric ozone layer, or as we popularly called as formation of ozone hole. So now, what are the problems if you have ozone hole widening, okay, or if the ozone layer is getting depleted? Friends, there could be varied range of impacts, and this impact can be on buildings, can be on animals, can be on plants, can be on humans. But what we need to understand is, these impacts are not because of ozone layer. These impacts are because of the ultraviolet radiation which has escaped into the atmosphere. For instance, these ultraviolet radiations are capable of interfering with photosynthesis. Eventually the yield will come down. Okay, now you know very well that you're not supposed to stare at sun. Okay, that's harmful for your eyes. In a similar way, too much of ultraviolet radiations can cause photokeratosis, or in simple words, snow blindness. Okay, now ultraviolet radiation is also capable of causing skin cancer. okay, that eventually would result in mutation. Now, not only this, when you have ultraviolet radiation more in your troposphere, it also aggravates or triggers the production of ground level ozone, which is another danger because it's a carcinogen. So friends, how can we go about controlling it? Okay, for your information, every year on 16th of September, it is celebrated as World Ozone Day. And that is because, okay, in on 16th September 1987, a famous protocol was signed in Montreal, that's in Canada, and very popularly called as the Montreal Protocol. Now, since the first ozone hole was discovered in Antarctica, which was on, probably 1979 onwards, okay, then further again in 1989. Okay, now what's happening is the ozone hole is becoming wider and wider. So since 1979, when it was first discovered over Antarctica, a lot of studies were carried out, and it actually presented that in the 18-year study since 1979, the ozone hole had become bigger by at least about 35%. Okay, now we need to curb this, we need to control this, and that is where the Montreal Protocol came in action. Okay, Montreal Protocol, which was signed by about 139 countries, okay, in the year 1987, okay, came with a conclusion, came with a ratification, okay, came with the objective that we need to ban the production of CFCs, and of course we need to talk about its replacement. Okay, the condition was that if at least 11 states ratify the protocol, then it becomes effective. And the effectiveness was from 1st January 1989. Friends, since that day to till this date, more than 160 nations have signed the Montreal Protocol. So what does this protocol say? The protocol says that, okay, from 2000, no developed countries shall engage in production of CFCs. From 2010, no developing countries shall produce CFCs. Okay, this was a decision which was taken, okay, in the Montreal Protocol. Now, if these actions were in place, even then we can only expect your ozone recovery only by 2065. Okay, please remember your CFC molecules have a lifespan of 100 years. You cannot control ultraviolet radiation, but yes, we can control the production of ozone, sorry, the production of CFCs. Okay, now friends, this document, which is popularly called as Montreal Protocol, is available in various languages. Okay, whether it's Chinese or French or English or Arabic or Russian and Spanish. So I would request you people to, probably download this on the World Wide Web and have a go at this. Okay, now what after your Montreal Protocol? Now that you are replacing, okay, now that you are replacing your CFCs, now that you are banning the CFCs, what should be done? Now this is something interesting that you need to be aware of. Now as an outcome of the Montreal Protocol, it was decided that we need to find a solution for CFCs, and unfortunately the solution that they came up with was called bromides. And very well now we know that bromides is 40 times more dangerous than CFCs. But luckily, okay, this has been identified and it has been halted. Further, what has happened is they discovered a new chemical which can replace CFCs, and that is HCFC, hydrochlorofluorocarbon. Okay, now hydrochlorofluorocarbon may not be a dangerous ozone depleting substance. Even if it depletes any ozone layer, even if it destroys any ozone molecules, that can be easily recovered by Chapman's reaction. So perfectly safe. But unfortunately, my dear friends, in the pursuit of finding a solution for ozone layer, we Homo sapiens came with a new problem. Most of us were not aware that time that Hydrochlorofluorocarbon is one of the strongest greenhouse gases which results in global warming. And that is why, friends, since the 1990s, let's say 1992, 1994, 95, 96, 97, 98, okay, you find the hottest years. That's because the global warming had increased rapidly since CFCs were being replaced with hydrochlorofluorocarbon. Now let's have a small video to see and enhance your understanding.
15 to 35 kilometers above Earth's surface, a gas called ozone surrounds the planet. The ozone layer acts as a barrier between Earth and ultraviolet radiation from the sun. However, pollution has caused the ozone layer to thin, exposing life on Earth to dangerous radiation. Earth's atmosphere is made up of 6 layers. The second layer, called the stratosphere, contains the ozone layer. The ozone layer is made up of a highly reactive molecule called ozone, which contains 3 oxygen atoms. Ozone is a trace gas in the atmosphere. There are only about 3 molecules for every 10 million molecules of air. But it does a very important job. The ozone layer acts as Earth's sunscreen, absorbing about 98% of damaging ultraviolet or UV light. But the ozone layer has gotten thinner. Chemicals called chlorofluorocarbons, or CFCs, are the primary culprits in ozone layer breakdown. A CFC is a molecule that contains the elements carbon, chlorine, and fluorine. CFCs are mostly found in refrigerants, aerosols, and plastic products. When CFCs are exposed to ultraviolet rays in the atmosphere, they break down into substances that include chlorine. The chlorine reacts with the oxygen atoms in ozone and rips apart the ozone molecule. Areas of damage in the ozone layer are often called ozone holes, but that name is misleading. Ozone layer damage is more like a thin patch, with the thinnest areas near the poles. The ozone layer above the Antarctic in particular has been impacted by pollution since the mid-1980s. There, the region's low temperatures speed up the conversion of CFCs to ozone-damaging chlorine. About 90% of CFCs currently in the atmosphere were emitted by industrialized countries in the Northern Hemisphere. In 1989, the Montreal Protocol banned the production of ozone-depleting substances. Since then, the amount of chlorine and other ozone-depleting elements in the atmosphere have been falling. Scientists estimate that chlorine levels will return to their natural state in about 50 years. By then, the Antarctic ozone hole will shrink to smaller than 8 million square miles.
So back to the presentation. So friends, what is that we have learned today? We have understood, some basic information with respect to ozone, what it is. We also were able to distinguish between the tropospheric ozone, the stratospheric ozone. We were able to understand the beautiful Chapman's reaction, which helps in the creation of ozone layer. We also understood how various chemicals such as bromides, CFCs, and oxides of nitrogen are on a mission to destroy your ozone layer. Also, we were able to understand what are the repercussions or impact when the ozone hole becomes wider, or as I say, it becomes thinner and thinner. Okay, friends, what we need to understand further is, as I told you, CFC, a miracle chemical which got a Nobel Prize for Charles Franklin and Thomas Midgley, okay, also got one more Nobel Prize for the 3 gentlemen you see here below, who actually were able to, find a solution for its replacement. Okay, so for the first time probably in history, you have Nobel Prize being given to a gentleman who discovered a chemical which led to a problem, and later to another three gentlemen who worked extremely hard to find solution to protect the ozone layer. So friends, I'm done with the presentation. These are the references for your kind perusal. Okay, please refer any material which you might find handy. Okay. In the further sessions, we shall continue with environmental pollution, and probably we shall be delving about water pollution with case studies. So friends, I'm done with the presentation. I thank one and all for your kind patience and hearing. And now I leave this forum open for any questions, any queries that you might have. Thank you.